some students launching rockets and building rockets. So I think he's busy now.
Okay.
I tried to
Wait
wait for him
for
to
him
to
to answer
answer,
our email,
but
but he didn't answer, so I think he's busy.
All right. Oh, you mean Rick Matchak? I did see that he might not be here.
Okay, let me see how I'm gonna get this working. Because I'm getting a lot of echo. Oh, I know how. Okay. Yeah, I think we're not getting echo now, right? No, we're not getting echo. Yeah, so I'm gonna monitor the recording over here. Yeah.
Okay.
Thanks. So,
Now, the
we
other folks would like a recording of this. Are you prepared to record?
yeah, I'm gonna start recording over here.
Okay, no rush on my part.
Yeah. Okay. So it's all recording correctly.
Okay.
The audio is being captured right apparently, and that's a go from me. Yeah, for me too. I'll start presenting our slides. We've made a presentation of
I would
our
love to see
rocket
it.
project. Yeah, just like last year. I don't know if you remember, Jimmy. So we're gonna present now.
Okay.
So can you see it? Can you guys
Yes.
see it?
I'm going to turn off my video to save bandwidth, but if you ever want me back, just say so.
All right.
There we go. Much better.
Okay, Jimmy. I'd like to thank you for your support. You're a great safety reviewer. Um, your tips were very useful to us, and we're really glad you're again our safety reviewer. So just uh I'd like to thank you in name of our team, and I hope this year you like our rocket again.
Yes. Well, thank you. And I should let you know that you're the most advanced team I'm working with this year. I'm just honored and delighted to be with you. I love my job, and you're the reason why. And your project is a really good one. I have a few questions about it, but nothing serious. Oh, that wasn't the rocket crashing, was it? Start over. No. Bad joke, bad joke.
Is Mike. Yeah.
But every one of you is smarter than me. I learned more from this, I think, than anyone else. I really look forward to seeing your presentation, looking at your rocket, and seeing it fly in a few weeks.
Thank you. Thank you very much. Okay, so beginning, this is our team presentation. We're team 133, and beginning with our project timeline, we began in September in 2023, and the first thing we did was defining the requirements of our project. We reutilized some parts from previous projects, but we've made some innovations. So we had to set up our project. We discussed a lot of things, and from September to November, we defined how a rocket would be, and we tried to see if the project would meet our requirements. So for 2 and 3 months, the stage of the project was like discussing things, making some tests, seeing if things were viable to us. And in December to February, we began the simulations. The first progress report was due on December, so we had to begin our simulations, and that's what we did. And yeah, we saw that the project was meeting our requirements. We saw the project was viable. Like we had a good rocket, and it was a goal to continue developing the project. And on February 20, and on February we've made our test launch. Our team builds smaller rockets so we can test some systems, and the main systems we test on this launch were the electronic systems, the locking mechanism, the new locking mechanism of the recovery module, and we had a partly successful flight. We had some problems, but all the systems we wanted to test were tested. So we consider it um, a successful operation, and we then went to manufacturing, and now we're making some final adjustments to our project. Like we're making some final adjustments to the on the on the rocket mass so we can meet our target apogee, and we're on the manufacturing stage. We're almost finishing our manufacturing. There are some parts that need to be finished, but we'll talk about it later. So the general characteristics of the rocket. Its name is Pacifico. It's a tribute to our late teacher, Tony Pacifico. Um, he was very important to us. He helped us with some projects. He gave us advices. So we thought it was a good idea and an important thing to pay tribute to him by naming this rocket after him. And so, uh, and we're trying to make this rocket especially good for him. And okay, so proceeding with the general characteristics of this rocket, it has a dry mass of 66.49 pounds. Yeah, we're not very used to the U.S. measurement system, so it's sometimes it's.
Oh, you can go metric on it if you like. I speak metric too.
Yeah, and its length is 8.43 feet, and we have an external diameter of 6.4 inches. It was it is different from the last rocket we launched last year. Juno 3 had an external diameter of approximately 5 inches. So now we're we're taking to the US a chubbier rocket, and that's an advancement compared to last year. This diameter made possible that we could have a payload in the format of CubeSat, and that's something we didn't do last year. So you can see the overview of the rocket. We now have the avionics bay inside the nose cone. So there we have the altimeter bay and also the telemetry bay, and number two, we have the recovery module. You can see it in the image, and below the recovery module we have our payload. And the last part is the motor, as you can see in the image. So we're presenting these modules in more details in the next minutes. But now we're going to talk about the open rocket simulation. And now Kyle will talk a little about it.
Okay. So now that we're talking simulations, we'll have to switch to metric because that's how the data is input into OpenRocket for us, and I think it's going to be smoother sailing from there. So we have a dry mass of 23.54. Oh, sorry, this is a mass with no engines. So, and I'm going to talk in the coordinate system oriented from nose to tail. So the center of gravity position is 166 centimeters away from the tip of the nose cone. And the center of pressure position is 210 centimeters, leaving us with a static margin of 2.67 calibers. Taking into account the rail button positions, we have an effective rail length of 4.12 meters. And the drag characteristics for the open rocket simulation were imported from Aero because we found that Aero does more sophisticated drag calculations, and that will lead us to a closer result to what we see in flight. And we compared it. We did this comparison with previous launches, because we're not used to messing around with open rockets. So we tested with previous rockets and figured out to get it as close as possible to the actual performance. And that's how we did it. So we're having an apogee, simulated apogee of 9,613 feet and a rail departure velocity of 23.6 meters per second. And okay.
And that's an upgrade for the departure velocity, which I'm really happy to see.
Yes, it's a huge upgrade, and Leo will get into more detail on this later.
Okay, good.
It's a great it's a great relief for us too, because we don't like to work around like really tight margins.
Yes.
So this is the complete flight simulation on Open Rocket. It's a little bit hard to see because of how Open Rocket organizes the axis, but in the next slide, I'll go in. It will have a close up on the boost phase. So there we are at our to 9,000 feet apogee. Here it is in meters. And in the boost phase, oh, I didn't turn my keyboard on. Okay. Okay, now it's working. So we have a close up here on the boost phase. And I accidentally cut it off, but the angle of attack at rail exit is 16 degrees. So which is, and it gets below 15.9 in a fraction of a second, which is the stall angle of our fins. And it quickly converges to near zero, which is expected and good. And we have the stability margin at the rail exit is right now 1.55 calibers, which is really close to the DTG limits, but we're looking into pushing it a little bit up with small ballast corrections on the rocket in the next few days, as we start to get the updated masses from the manufactured components rather than the CAD model. And then we can do a finer tuning of these calibers. And yeah, the rest is over there. The vertical velocity, we're at a maximum of around 250 meters per second, which is Mach 0.755. And our vertical acceleration is around 14 Gs, or maximum acceleration.
Cool. I have a question.
All right.
The purple line that's bouncing up and down at the beginning, what does that represent?
That is the angle of attack. So as this simulation is done with specifically high winds, so it's 6.7 meter per second winds. And so as the rocket goes out of the rail, it hits this angle of attack from the wind that it didn't have before, and it oscillates a little bit before stabilizing on its final trajectory because of the sudden change of angle of attack.
Right. Well, I'm glad to see it straightened out quickly.
Yeah. So we're working for future competitions to do a deeper analysis on damping coefficients for angle of attack. But right now we're not really so confident on working with this analysis because we didn't dive deep enough into it. So we're looking at this for next phases.
Is that something you'll add to Rocket Pi?
Damping coefficients? Right now, not yet, but we're talking with the team because now Rocket Pi is not from Progetto Jupiter. They have emancipated from us. So
really?
Yeah, that has been I think 1 or 2 years ago. Yeah. So they have their own team from people that are not. Some people are from Jupiter, Progetto Jupiter. Some people are not. And the managing right now is not on the team. So we can talk to them, ask for new features, help them in improving features, but they are now also working with teams all over the world, and they become the official simulation software for UROC.
Okay.
So we're not so close to them anymore. But we
Yes.
still use it because we're more familiar with the interface and the outputs. But we fully understand that you prefer this because it's just like another form of presenting data, and it's a lot less gibberish in code. So it's fine.
Yes.
So I'm gonna go over to Arthur. That's gonna explain the electronic systems in this rocket.
Okay. Good afternoon, guys. Good afternoon, Jamie. I'm
Hello.
Arthur. I'm the leader of the electronics team in Projeto Júpiter, and I'm gonna give you an overview of our systems for this rocket. And in previous rockets, the electronics of the rocket were very spread out throughout the rocket. We had the telemetry with payload; it was part of the payload, and we had two different modules, identical ones, to activate the ejection systems, the recoveries events. So we had, one set of altimeters for parachute ejection below the parachute, and then in the nose cone we had another set of altimeters for the disreefing event. And I think Caio is gonna go further into this in the recovery section. But then we were able for this rocket to invert the recovery. You can see in the images the cartridges are now in the nose cone pointed down.
Yes.
And then we were able to put both of the recovery events in the same module. So we only have to use two altimeters, the COTS and the SRAD, of course. And we also brought telemetry up in the same module, which is better for us as a team to work with the same module. We don't have to integrate that much with other areas. So overall, it's a better design for us. You can. So the module itself, it's mostly 3D printed. We have some aluminum discs to support them. And it's supported on top of the cartridges and with threaded rods and nuts to lock everything up. It's very solid. And we also have those key switches. It's kind of an schematic view, but they are on the fuselage. And we have four, each of them for a different system to, make things independent and redundant.
Mhm.
You can pass.
May I ask
Yeah, sure.
what material you're using for your 3D printed parts?
It's PETG.
PETG?
Yeah.
Okay.
BTG.
Yeah.
Okay, so it'll probably hold up in the heat.
Yeah. And in our test flight that we mentioned earlier, which was a ballistic flight, all the boards survived the ballistic flight.
Oh, really? Wow.
Yeah, which was kind of surprising, but great nonetheless.
Well, very good. Very good.
Yeah. Okay, I think you can pass. So the top structure is just like a vertical wall, and it holds the SRAD telemetry board. On one side, it's like screwed in with thermal inserts. In the Juliana is showing the module.
Yes.
And on the back of the wall, we put the batteries. We use two lithium-ion batteries to power the board in series because transmitting requires a little bit more power. And I think that's it. And we have a top disk just for protection from any debris or anything. But that's it. Okay, and the bottom structure, it's triangular. We have three 3D printed walls, and they fit together, but they're also independent. We can take one out and work on the circuit and change the batteries or something and put everything back together. And, the first wall, it's the COTS altimeter, the RRC3, and I'm going to talk about it later. And the other one is the SRAD altimeter, and finally the featherweight GPS, which is the COTS GPS. And they all have a battery, a lithium-ion battery, to power them independently. And I think
I have
that's
a
it.
question about the battery connectors, the battery bays.
Yeah, sure.
Are they reasonably immune to inertial forces?
Yeah, they are screwed in with thermal inserts behind the battery, and then we
Okay.
put the walls have holes in which we fit zip ties. We put zip ties tightly to secure the battery so it doesn't fall out.
Okay, and it can't move forward and backward and temporarily disconnect, right?
We had this problem once, but
Yes.
we solved them. Firstly, we put the spring of the battery housing down, so if we have a like a downforce, it it works with the spring to don't disconnect.
Mhm.
And we really tight the ziplock, like really tight, so that the battery really can't move.
Okay. Well, good. I've just seen that kind of failure several times with that type of, not that exact battery box, but very similar ones. I'm
Yeah,
glad.
Yeah,
we might have been one of them in 2019.
yeah, we
No,
had this problem.
we
Yeah.
had this problem last year on
But
last cycle.
oh yeah,
Yeah,
actually, and but I think it was on landing, not on flight.
it was on ejection,
Injection,
in
okay.
the injection time.
Yes.
When the parachute ejected on January 3, the COTS battery went downward and backward,
Oh.
downward and upward. So it resetted the altimeter, and we had some problems when 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 the organization asked us about the apogee, because the flight data was a little bit messy, but it recorded the flight data until apogee they caught,
Okay.
and so we managed to talk to them and they accepted our apogee. It was
Good.
true. It was a true apogee. It was just messy after the
Yeah,
apogee.
because we had a data corruption that set
Yeah.
a fake apogee because it was just a single data point at 30,000 feet,
Yeah.
and the next point was 6,000 feet below ground. So
Oh.
yeah, those are not really trustworthy data points. Those are kind of outliers.
Oh.
Okay, so this is our new board. It's the SRAD telemetry board. It is like fully designed by us during this cycle, 23-24. We had it professionally manufactured in China. It was like a partnership with them, with the company. And then we soldered all the components and tested the board. It's also flight tested in our mini rocket flight. And we had really good results. We didn't lose signal with the board. We had GPS position, we had pressure, gyroscope, accelerometer, and it's based on the STM32 microcontroller and a bunch of sensors, and then the LoRa transmitter. And I think that's it.
Okay. It's pretty.
Yeah,
You do good work.
we're very proud of it. And then we have the receiver board. This one we made ourselves in our lab. We are also very proud of it. It turned out really pretty. And it just, it's just a receiver, and then it sends the data to the computer for the interface, which is the next slide. Our interface, we're actually going to use this for the live video challenge. We're going to plug into the stream of the competition. And it's an interface. We can see the data that's being transmitted from the rocket on the computer for a better visualization. Okay, so the COTS telemetry is the featherweight. It has an independent battery, as you've guys seen, and an independent key switch, and it sends GPS data for the ground station. It's pretty simple.
Good.
And then we have the COTS altimeter, which is the official apogee logging system. It's we have worked with it for, I think, ever since Jupiter existed. We have loads of experience with it. And I mean, it also has its own battery and key switch,
Right.
independent. Yeah. And then this is our novel S-Rad altimeter. It's actually the second version of it. We made it at the same form factor as the RC3, which is the COTS,
Yes.
to make them interchangeable. If we have any problems, we can just put a COTS one there, like two COTS, not like one S-Rad and one COTS. And it's kind of similar to the telemetry board. It's the same microcontroller, the same barometer, but then we have data redundancy. We have two different storage modules in the board, and we have designed some circuitry to make the board better than the first version. We have image detection and reverse polarity circuitry. Sorry, in case we connect the batteries with the positive and the negative, which has happened, and we fried one board.
I've fried some things that way. Yes.
Yeah.
Can be done.
Really sad. And we have now a USB interface as well to make things easier for us to acquire the data and to program as well. And you can pass, I think.
It's also pretty.
Yeah. Quality in the making of PCBs. So the software it runs, we also have tested it many times. It's an adaptive filter, and it takes the discrete pressure data and turns into a parabola, and we compare it to a reference parabola to find the vertice of the parabola, and then we can find the apogee. We have worked with it, we have launched it, and it works, and we are very confident. Yeah, and then in the graph you can see the filtering that it does, and it takes the noisy data and turns it into like a smooth parabola as best as possible.
That's very interesting to me. Let me turn on my camera for a second. Where'd it go? Oh, there it is. Oh, yeah, here we go. Here's something I'm developing. It's an altimeter to fly on a model rocket with a C motor. And it uses a Raspberry Pico and a couple of chips on the other side. So it's like $10 worth of parts to put it together. The main deficiency of it is a very simple program I'm using to control it. Doesn't have any kind of error correction. So it's not very accurate. So I was very happy to see your description of the way your error correction was working, because that helps me understand it a little better. So I thank you for that.
Oh, that's nice.
Is it open source right now?
This, yeah, this is. It's very simple, though. I'll send you what I've got on it.
All right, that looks great. It's the beginning of something great, I think.
Well, I hope so. The fact that it'll fit in a tube that flies on an Alpha rocket.
Wow, that's tiny. All right.
Significant, because we can fly it here on campus and fly it with youth groups, and we're using this with our physics classes. They're using it to bring the data back and practice doing analysis with it. So,
yeah,
okay,
that's great.
I'll see you what I have on it.
Okay.
Okay.
Okay, so this is the testing we do of the altimeter, one of the tests, and it's the simulation, the ground flight simulation test. So we get the pressure curve, the simulated pressure curve with noise, and we feed it to the algorithm as if it was coming from the barometer, but it's not. It's pre-coded, it's hard-coded, but we treat it as it was coming from the barometer, and then we just let the code run, and we see if the stages will be detected and activated, and we see if it will beep the apogee as it would in a flight condition. And then I brought the video for you guys. I don't think.
Wait, is the sound coming through, Jimmy?
I don't think so.
Okay,
I
just
hear some sound. Hear a little beeping. Oh, okay. I saw something.
I'm sorry for the long video, but it's like really the flight simulation.
Oh, so this is the time that the full flight would have taken.
Yeah, yeah. So
All the
the
way to
first,
the
yeah, the first one was the apogee,
Okay.
and then this riffing is gonna happen in a while.
Okay.
Yeah.
More fireworks. Yay.
So that's what we do to test if the algorithm works with the pressure data we are expected to have.
Excellent.
And then we have the wiring and assembly of the module. This is the mini rocket that we launched in I don't know, our flight in not a competition, sorry. And we always use a color code to wire the boards. You know, the key switch for each board has a color. The connection to recovery has a color for each of the systems, you know, as red and COTS, main and drogue, which is, you know, apogee and this riffing. We use the screw terminals to connect the wires to the PCB. It's the boards. And then for crimping the wires, we always use just the metal tubes without plastic and the heat shrink transparent to make things visible and to see if the connection and the fixation was good. I think that's it, guys.
okay. So I didn't present myself. I'm Kyle. I'm the recovery leader of the team, and I'm going to go over the recovery system that we're boarding on this rocket. So a quick overview. It's going to be a reefed quadrispherical parachute. Then I'm going to go through the linkages and shock cords, the CO2 ejection system, sharping locking system, which is brand new,
Okay.
pyrotechnic disreefing system, and I'm going to go over the performance on past flights.
Okay. Excellent.
So this is our main parachute right now. It's a quadrispherical parachute with a reef diameter of 4.3 feet and a reef drag area of 13.1 square feet. This reef diameter of 10 feet, and this reef drag area of 70.8 square feet.
Okay.
So this is it. And the first event will be trigger apogee, which will be the parachute ejection. So it will be ejected out of the rocket in its reefed state, and it will cause an opening force on the force section of the rocket, which is the nose cone and avionics bay, of 163 pound force. Is that how you say it? Pounds force. And on the aft section, which is the payload and rocket engine, it will be an opening force of 270 pounds force. And the terminal velocity during the rift stage will be of 72.2 feet per second. And the second event, which will happen at 14,000 feet above ground level, is the disreefing, in which the parachute will reach its maximum diameter. And we're expecting an opening force of 201 pounds force on the force section and an opening force on the aft section of 489 pounds force, and a final terminal velocity of 30.4 feet per second. So this is how the linkages are structured for this rocket. I can show some things because they're all laying around on the floor here. And
Okay.
so this is the riser with this is the part that will connect the parachute to the rest of the rocket. So here we have the carabiner that will attach to the parachute, the mounting structure for the line cutters, and the wiring harness, not the attachment points for the wiring harness for the disreefing, which are those little loops over here on the riser.
Okay.
Oh, sorry, shock cord. So all the connection points to the parachute and to the rocket are going to be done with quick links rated up to 1,350 pounds force, and we're going to use a swiveling link like this. I think you can see it. Also rated to 13,500 pounds force. And the shock cords are made out of tubular polyester, rated to 3,600 pound force. And we stretched them quite a bit from our first progress report, as you and Rick commented that it would help absorb some of the opening impact on the connection points. And all the stitches on the connecting points are done with polyamide threads. This is improved. This is the same method that we have been using since 2022, with a little bit some improvements here and there to make it stronger. So we increase the hold over length here on the loop, so that it can withstand higher forces without tearing the stitches. But in 2022, we had a rocket Juno 2, which had really comparable forces, and we saw no deterioration whatsoever on the shock cords. So this is the ejection system.
Can we back up to that for a moment?
Of course.
Because this is the one concern I have about this system. Now, you've flown this, you say, a couple of times and successfully?
Sorry?
Have you flown with this configuration, you say, a couple of times?
So this exact configuration is new to fix the problem we had last year. So we changed the position of the swivel link due to a problem we had, because we had the successful ejection, but at some point the swivel link used to be here where the parachute connection point is.
Okay.
And what happened was the parachute started twisting for some reason, and that led to the reefing control line to start kind of choking the parachute, because it doesn't go, it can't swivel. It just goes around and round and round. And as the parachute spun, it started choking the parachute. And at this reefing attitude, the control line was cut, but due to friction with the suspension lines, because it was wrapped around it like an anaconda, it couldn't slide and the parachute didn't open. So we read some technical reports from other teams to search for solutions to this. And we saw that a more common swivel link position was not on the convergence point of the suspension lines for teams that use reefing. So we moved it down. So in this way, if the parachute starts twisting, the whole line cutter assembly and wiring will twist alongside with it, and we'll have no tangling. So we did ground tests of this, in which we hang everything up to the ceiling and try throwing things around, making it spin, making it twist. And we did not see any twisting on the parachute or any of the important parts, only down the larger 14 feet length, which can twist as it wants because it has no essential connections on it, except from the mechanical connection of the shock cord, which is not a problem.
Okay. Well, here's a question I have. You've got your shock cord, of course, going from the rocket up to the swivel, to the wink on the base of the parachute, the shroud lines.
Okay.
You have the line cutters just a little bit down from that, and you'll be needing to run an electrical cable from the rocket to the line cutters, right?
Yeah.
What's going to happen to that line when the rocket and the parachute turn in relation to each other? Your shock cord has a swivel in it, but I'm going to bet your electrical cord does not.
Yeah, so even though it doesn't have, that was one thing that we observed in last year's edition, that the attachment points that we made are not susceptible to twisting. And so everything was twisted up, and the electrical connections were just fine, because we sized them appropriately. So they're a little bit longer than the shock cord itself, but not with that much slack that it can get caught on anything. So if twisting happens, it just runs along with the twisted shock cord, and it does not break. the crimping connection survived. I can show you pictures of this later. It's not on the PowerPoint.
Okay.
But then you can see, and we tested the connections after with a multimeter, and everything was fine. So all the flights we did with the same configuration, or at least this shock cord right there. Even with the swivel link in the other position, this shock cord also had twists on it, but it never affected the electrical connections.
Okay, well, I hope it doesn't this time. I still see a potential problem there, so recommend thinking through this, because if you have one cord that's swiveling and the other can't, if the two items turn in relation to the other, it's going to put a lot of torque on a lot of pull on the electrical cables when they start getting tangled around the shock cord.
Okay, we'll look into deeper tests into that. I'm pretty confident in the system, but if you feel like it's better, we can report to you and Rick how these tests have gone. So we'll record it and show and send it to you via email.
Yeah.
So
well, here's a possible solution. I've never done this. I've never done the kind of reefing you're doing, so I'm really a baby about this. But one thing I have seen with such things is you put a lot of slack in your electrical cord and you zigzag it at several different points. So if it starts getting twisted, it won't get tightened very quickly.
Oh, I see.
It'll have extra slack in it.
Yeah, it's sort of analogous. It's more tidy than what we do, but it's not that different. Because I messed up. I don't have the wire. Oh, okay, I have some wiring here. I can show it to you how the connection is done, because this is a riser that has a load cell that we use to measure parachute forces.
Oh, okay.
It's not flying on this rocket, the load cell, but we fly it on our test rockets to make sure our systems are validated. But sadly, it hasn't worked yet. There's always a new problem.
Yes.
Yeah, I don't think I'm going to be able to feed it through right now, but I'll show you in the end of the presentation while someone else speaks.
All right.
Okay, so moving on to the ejection system.
Yeah.
This is our good old trusty CO2 discharge ejection system. And so we have a main charge of 45 grams and a backup charge of 45 grams, which we know is a lot compared to what other teams do. But it has worked for us. It has given us plenty of clearance at ejection. And since we are changing some things in the overall rocket layout, we're working with a larger diameter. We rather have ejection that's more powerful rather than one that's not powerful enough.
Yes, I agree.
And it's especially since we're using shear pins, so we really want to make sure that they will break. Yeah. So it's a redundant activation by CODs and S-rod altimeters. The ejectors are wired in parallel to each ejection system. Sorry, each altimeter. So if one of the altimeters fail, both ejectors will still trigger, which is great. So that means we can have one altimeter fail and one ejector fail, and still have a successful ejection. And we have where did I leave it? Oh, I messed up. Okay. Okay, we have a PETG piston that helps push everything out, which is this one. And it goes on top of everything here. It touches the connection, and it helps create a stronger pushing force that ejects everything successfully. Okay, Juliana figured out the wiring for me here.
Oh, good.
So it goes through a loop like this. And we can leave some slack between the loops.
Okay.
So if it twists, it doesn't rupture because it's looser than the shock cord itself.
Okay. Yeah, that looks good.
So it's still connected. There's no problem. If it untwists, it untwists. And we just are careful to not leave a lot of slack so that this doesn't get caught in anything and rips out all the wiring harness.
Well, if you want extra slack, you zigzag it and hold it down with masking tape or something that keeps it in place.
Oh.
Or something you can slip out of.
Yeah, we didn't think about that. That's great. Oh, I think we'll use that because it's cheap and it sounds like it works.
Okay.
So
No extra charge.
yeah, and about passing slides on the wrong computer here. So here we have some ejection tests. This is on our previous rocket that we would launch in the 2023 Latin American, which was our first experience with 6 inches. We're speaking in Portuguese in it, but it's 2 25-degree cartridges on this configuration right here. And this is the old configuration in which the nose cone would only house half of the avionics bay. It is a successful ejection. We always test our ejections vertically to make sure it's the worst possible configuration compared to horizontally. So we have everything fighting against the ejection. And this is the recent test, which is in module is the same, but it's in the new configuration with the new system and everything updated, which is plenty of power.
Wow. And you're starting a new sport.
Yeah, we're starting a new sport because we don't want it hitting the ground and breaking before the flight.
Right.
And we had 2 accidents before in which the top module fell down on the sliding coupler and cracked it. And it always happens like right before the competition. It never happens with some time for us to fix it. So we rather be catching them in the air.
Yes.
It's quite fun. So okay. And okay, I already showed the video. Okay, the locking system. So we're now using 4 M2 nylon sharpings to keep the module locked. They go through the fuselage, they screw on the fuselage, and then go into the sliding coupler. And that keeps the module locked. I have a baggie of them right here. They're really teeny tiny screws.
I'm familiar with them.
So yeah, and it was a surprise to us how little force actually happened during flight. So the maximum separation force we have in flight is of 7.5 pound forces, which we calculated with a mix of RAS aero and open rocket. So we've got the RAS aero curve, but it simulated, got the maximum drag force along the flight, and using the component analysis on open rocket to see how the drag is distributed along the rocket. And with that, we could calculate the separation force on that specific coupling. And it's 7.5 pounds force. But that's small. That's a bit over half than the handling force that we can have just moving the rocket around on the ground.
Yes.
And that would be a problem if the sharpings broke before the rocket had taken off. So we took that into consideration. The maximum handling force. We did ground tests with the sharpings. They withstood wonderfully up to 16.3 pound forces and broke when we added mass on top of it. So we did this test with a little bit of an impact. So we lift the mass a tiny bit and release it just so we have a bit of impact and we're not working on that quasi-static configuration in which creep happens, which is not interesting to us because we're really talking about impact there. And so it was ground tested. The last video that you saw from the ejection system that went way up, it was with the Sherpins. So the ejection system is more than capable of breaking them in flight. And the flight that we did in the beginning of the year, that was our test flight. We flew with 3 nylon Sherpins, which was according to our calculations at the time, and they survived the flight. So it survived all the points, survived the maximum drag force to apogee, but due to unforeseen circumstances that we can get into later, the ejection system wasn't triggered. And not even the COTS system detected the apogee, which was interesting. Yeah, it was. We'll get into it later.
Was that at a competition? I missed a little bit of that.
No, this is our self-operated flights that we run only for testing subsystems.
All right.
And this is the disreefing system, which is pyrotechnical with black powder. It's really simple. It's a sort of a brute force approach I have one assembled here. So we use the paracord core strands to run into this black powder chamber, and it fits over here on the harness. Yeah, with the screw it won't fit, but it goes into here on the shock cord. And it when it's triggered, it just blows up the strands, and the paracord is free to run away, and this allows the parachute to open fully. So we have one charge of 1 gram, and we have another one. They are in series, so they go one on top of the other. And if one ruptures the port, it can run through, and so we have redundancy there. And they are also wired in parallel with the CODs and SRAD altimeters.
Okay.
And the wires are fed through the loops on the shock cord, which I showed you. And to avoid tangling and excessive tensioning, so that it doesn't rupture in flight.
Okay.
And so the past flights that we had with the system, we had a nominal recovery on 2022. And in the test flight in 2023, in which we had ejection, it was the first occasion in which we had the wiring harness rupture due to a miscalculation of wire length. And what we added to the assembly routine was what we call a stretch test, in which we lay everything on the floor, pull the nose cone as far away from the rock until everything stretches, pull from both ends to see if we have enough slack, if it's not going to rupture just on the opening force. And in 2023, as I mentioned previously, we had ejection. We had the briefing was triggered, the control line was cut, but it didn't slide due to the twisting of the shroud lines of the parachute. And so we fixed that by changing the swiveling position. I don't know if you're aware, because I don't think you are judged in this category, but we took inspiration from Waterloo University and how they function swiveling. So our system in theory is as effective as theirs in surviving twisting of the lines. So I hope we have no problems. They didn't have a problem. Oh, and I hope we have no problems. We're testing this on and on. And I'm still passing the slides on the wrong computer. So that's it.
Well, thank you.
I think you.
Good afternoon. My name is Felipe, and I'm a member from the payload team.
Hello.
So I'm going to talk about a little bit about the system in general, the experiment that we're bringing this year to the competition, the cameras we're using, the structure and the fixation, and our camera motion system that is related to the experiment itself. So our experiment this year is called Tiltado, and it is an acronym for the image leveling, tracking, and attitude determination operator. We thought about the letters for a lot of time, so that we had something that made sense.
Sounds like it's tilting.
Yeah. So the main goal of the experiment is to develop these video capturing systems on the rocket on high vibration and acceleration, so that we can maybe in the future experiment with computer vision experiments, and so we could have better systems for marketing purposes, for cameras on the rocket to record the flight. That is something that we weren't able to do yet, the in-flight video recording. And we're also gonna work with attitude estimation of the rocket and control systems, and we're gonna do that by controlling the axis of the camera that is attached to a motor and that can rotate on its axis. And the objective of the experiment is during the flight, we're gonna try to maintain the horizon line level with the camera in relation to its reference system. So the experiment detects the attitude of the rocket and rotates the camera to counteract the effect of the different orientations and to make not actually stable because it's going to be rotating a lot, the rocket, but we're going to try to maintain the horizon leveled.
Okay. Can I ask a question?
Yes.
Is this expected to work only in boost to apogee going up, or is it going to work in descent as well?
Our objective is to work in boost to apogee,
Yeah.
and with it should be able to actually when the rocket is detached, actually attached to the parachute and rotating, I we can't guarantee the experiment working, so we're counting on it working from the boost phase to the apogee.
Okay. Well, descent will be your next challenge.
Yeah.
Yeah. Excellent.
So for the experiment, we have two fisheye lenses cameras that have a field of view greater than 180 degrees, and they are located diametrically opposed. And we're going to use these cameras, and we hope to merge the footage to obtain some kind of video capture that has a 360 footage of the rocket launch, but also the videos can be used independently. And for these cameras, we also have a camera positioning system that I'm going to talk in the next slide, because if the cameras stay too close to the structure itself, they're going to record the inside of the fuselage.
Okay.
So we're going to have which is a problem usually with these cameras that have very high field of views.
Okay.
And we're going to do a system to push the cameras outwards for that, so that we don't record no fuselage or close to no fuselage for the video quality and also the experiment evaluation post flight.
Okay.
So our structure follows a CubeSat form factor, a 3U CubeSat, and most of the structure, the outside structure, and is all manufactured from aluminum, and we have brass standoffs between the different shelves of the system, and the fixation with the rest of the rocket. We're gonna have four M5 screws that are screwed. They are screwed through the rocket coupler and on the four corners of the CubeSat. So we align the whole structure, and we can screw the four corners of the CubeSat so that it maintains it is very fixed and stable with the rest of the rockets.
Very good. It's also very pretty.
Yeah.
Oh,
Yeah.
there's your mechanism for moving it.
Yeah. So this is the mechanism that I talked briefly about. So as you can see, we have four NEMA 17 motors, and they're split in two. We can split them in two groups. Two of the motors, as you can see, have the camera attached to them, and they are the motors that are responsible for the rotation of the cameras on its own axis. And we have a mechanism, as I said, to push the cameras outwards, so that we don't have this limitation of the recording of the fuselage. That was something that we implemented kind of similar last year, that we also had an experiment related to cameras. And one of our problems in our test flight in 2022 was that the cameras recorded, due to the field of view, the cameras recorded a lot of the fuselage, and the footage could have been a lot better if there wasn't that much fuselage. So we do this so that we can have hopefully the recording of only the outside of the rocket, and we have I hope a very cool footage, especially for our team that never wasn't able yet to record on-flight footage of the rocket, and it is something that we really want to do. And yeah, this is the whole experiment. And we can back up a little bit to slides. I think pode ir para frente, one forward. Yes.
I look forward to watching the movie.
Yeah.
Yeah.
I think we have the empty shelves in this photo, but they have yeah. Now we have a photo that is newer, not newer, but with the components.
Okay.
And we have a structure of the payload inside the CubeSat form factor, organized in shelves. That helps a lot with while you're putting together the system. And the basic premise of the main parts of the system, we have the power supply. So we have actually 8 lithium-ion batteries, and these 8 lithium-ion batteries are split into different power supply. There are different power supply sources. So we have 4 of them that are going to be used for an independent power supply for the motors, 12 volts. And we are going to have 3 of them, 4 of them in series. Sorry, but we are going to have 3 of them for the main electronic components of the system, and 1 of them that is going to be for the third PCB board that actually isn't directly related to the payload itself, but is an experiment that we're doing for our group. And a little bit about the components for the controlling of the cameras. We're going to use for each camera an independent Raspberry Pi Zero. that records and stores the data, and they are used just for the recording of the recording of the data. And we also have a Raspberry Pi Pico that controls the motors, and also that does all of our computing. And we have a MPU 9250 that has the three accelerometer, three gyroscope, and three magnetic axis measurements. And from the accelerometer data, we derive the estimation for the attitude. And from this estimation, we can calculate how much the cameras should turn. And yeah. And the other PCB, just for curiosity, is an experiment that we're trying to do with is a PCB for a Kalman filter data logging, and we're trying to experiment for research purposes. Eventually, the development of an air brake systems. We don't know. We can dream, and this is the first step. So these third PCBs is independent, but as it is there, I'm just gonna tell what it is doing there.
Yes.
And that's basically it. And for the system, we have a key switch that turns on the payload experiment, and a separate key switch that turns on these Kalman filtering data logging experiments.
Yes. Excellent.
And that's the overview of our payload this year.
That's beautiful. I hope it works.
Yeah, I hope it's so.
Yeah.
Yeah, thank you.
Hello, I'm Leonardo. I'm the leader of propulsion team. Good afternoon, everyone. Good afternoon, Jimmy. So I'll be passing an overview through the propulsion systems. So you get general information about the motor, the structure and its analysis, the tests we made, the simulations for the design of the motor, then the motor parameters, and another flights that we use that motor. Actually, it's the same motor that we used last year in June 3. So okay, we can pass on. So it is a SRAD solid motor, yeah, with 5 KNSB grains with Bates profile. We use Kevlar, resigned Kevlar as inhibitors, and one little change then we made it from last year is to use fiberglass as liner. Last year we used EPDM rubber. So with fiberglass, we had a better fit for the grams.
Okay, good.
And a 9mm MDF spacer between each grain. So for the structure, we use 6101 aluminum casing with 2 lines of 16 M6 steel bolts for the nozzle and the bulkhead, 2 O-rings and each closer for sealing, and the bulkhead is made of aluminum 6351, while the nozzle is 1020 steel.
Okay.
We also have the chamber.
We also have the chamber.
It's a big one.
Good. I like big ones.
It's a bigger rocket.
Yes.
So for the structural analysis, we analyze the both shear, both tear-out, bearing failure, case tensile, and von Mises youth failures. And for the analytical analysis, we got the lowest safety factor of 2.2 for the bearing, and in the finite elements, 2.48. Okay, passing for the hydrostatic pressure testing. So we, with a hydraulic pump, we hold a pressure of 90 bar inside the chamber for 100 seconds to verify if there was any leaking or any damage for the structure.
Good.
Okay, and for the ballistic simulations, we actually use our own open source software, SolidPy, developed by the team, using unidirection isentropic flow for the ballistic calculations, and in which we get the burn time, specific pulse, stress coefficient, and we in the software we can use customized core geometries. And the results for this motor was cross-checked with OpenMotor. So this year we managed to make another test fire test, and that is showing the following video. Yeah.
Ooh, love that smoke. Okay, very nice.
A lot of smoke. Yeah, in which we are able to measure the thrust and the chamber pressure curve. So passing on, we as I said, this motor was here are the general parameters, right, for the motor. So we have 17.9 pounds of propellant with a load mass of 34.4 and a burn time of 4.3. That was a little improvement from last year in burn time. So we got a lower burn time and a higher max thrust this year in this year test. So as I said, this motor was used on previous rockets. So Passion will have nominal operations. So in these both competitions happened in Brazil, the Corbroof and Lasky. So this motor actually it was born in 2017. So it's a little old motor.
Oh,
and so the motor was used in Pirius in Corbroof and in Juno 2 in Lask. And below we have the following videos of the launches.
Oh. Wow, nice.
Yeah. And for Lask launch.
Ah, okay.
So
and for last but not least, of course, last year we actually used on SA Cup. So here are the video for the launch.
Okay. Very nice. I love your movies.
You never get used to it, right? Yeah, so that's the propulsion section. We actually how we pass we use the same motor as last year. We passed this year since last Spaceport improving our propellant manufacturing. So
Okay.
in that matter, we were able to achieve some improvement in thrust that result in a better rail velocity.
Yes. It looks like you have a very well developed motor, and apparently you've mastered the making of propellant. I'm proud of you for doing that.
Thank you.
Okay. Hi, Jimmy. Hi, everyone. I'm Felipe. Another Felipe, yes. And I'm gonna talk about the aerodynamic surface and some structural bodies of the rocket. Yes. Uh, there is an overview. Yes. I will talk about nose cone, fins, bow tail, fuselage, couplers, rail attachment, and structural analysis. Yes. Uh, I'll begin with the nose cone. The shape of it is von Karman, yes, from Hex series. Kyle will show it to you now. Uh, the total length is almost the curve section is almost the total length, yes. Just a straight section to attach with the couplers, yes. Uh, the fineness ratio and bluffiness ratio are there. Yes, 3.69. Usually we think like higher than 3 is a good fineness, but next to 4 it's better. Yes. So this year we usually use a higher one, just like 3.9, like 4. But this year we choose a little bit lower because of the manufacturing. Yes,
Okay.
because this year I would say yes, we used some vacuum lamination, and we divided the mold in two parts. Yes, because it's a difficult shape to laminate in with hands. Yes, so we need to divide it in two. Uh, it's made of fiberglass and epoxy resin. And last year we used it 3D printed because of the shape of the nose cone, but it has some problems. It's heavier than this one, and another project problem that the last nose cone was made of PETG, but was reinforced with fiberglass. But the part that we attach with the couplers were not reinforced because we need to use the adhesive in the place. Yes. So in this year we changed it because become lighter and it's better in its structural function. Yes.
Okay.
You can pass. Uh, Now I will talk about the fins. Yes, we use an airfoil in our fins. Yes, the shape of the airfoil is not 012. Yes, I don't know how to say this in English. Sorry, but we do something new in this. Just that we use it in the last project of SACUP. That's we call it truncated. Yes,
Mhm.
it's like a cut in the section in the final section of the airfoil. Uh, the main result of it is that becomes stronger because when we need to recover the rocket, it need to be uh, becomes how can I say? It needs to becomes like uh, sorry, I forgot the word now. It's uh, it's for the purpose is structural, yes, and it needs to be like the tip of the airfoil.
Mhm.
It's hard to not break, yes.
Oh,
We have
yes.
some other cases that the tip gonna break. So we reduced a section of the airfoil
Mhm.
that could be better for don't have some imprevisibility in the flight or to reparation points, recovery points. Yes.
Okay.
Uh, and we did some CFD tests to know about the difference, and the drag difference was minimum. Yes.
Mhm.
So
Yes.
it's not significant. Yes. So we used the shape of the things that are clipped delta, yes, trapezoidal,
Mhm.
and the root chord and tip and span are right there. Yes.
I have a question about how the fins are mounted.
Yes, I will show in the next slide.
Oh,
Yes.
okay, you're getting there.
No, no,
Yeah,
it's okay. It's okay.
perfect. Good timing.
About the manufacturing of the fins, the airfoil are printed. Yes,
Mhm.
and the fins core are made of carbon fiber. Yes.
Yes.
Uh, the motive is it's hard to manufacturing the airfoil, so we need to 3D print it.
Mhm.
But for the a better resistance, we use the carbon fiber core
Mhm.
in the middle of the things to have a bit more resistant. Yes, and we attached the core and the things, the core and the airfoil with the same glue, no, same adhesive that we use in the couplers and in the
Okay.
tubes. Yes. Another thing that we use in the attachment of the things in the rocket, yes, are using a chip-to-chip method to reinforce the section. We know that is very fragile in the rocket, just this part of the attachment. So we use it the reinforced with fiberglass, and some holes we fill with flux, yes, the cotton fiber.
Mhm.
So we don't have problems with it.
Okay.
Yes, like showing the image.
Yeah. The question is, you have the solid core of carbon fiber. Is that attached to your airframe directly?
Uh, yes.
Okay.
Uh, we do like a in this image we you can see, yes, but there is a hole that
Yes.
come back an image, Kyle, please. Uh, we can
Uh,
you can see that has a section that are higher than the fin span, yes.
right. A tab.
Uh, yes, and we use this to attach in the rocket. We do a
Okay.
hole and we fix it with the glue, and we do another reinforce with the tip to tip. Yes.
Just
Good.
so just so we make sure that we're not hitting a language barrier. The core sticks out the bottom and it fits into a slot on the fuselage, and
Okay.
it's screwed there with the adhesive.
Yeah.
So we have the core attached to the fuselage and the tip-to-tip lamination.
Okay. Good. That's what I hope. Now, this picture, I have a question about it too. It looks like you're just getting started with the tip to tip. I assume that the fiberglass will go all the way over the fins and down the other side.
No,
Yeah,
we just do it in the intersection sections. Yes, not
Okay.
all over the fin, just in the
but
intersection.
yeah, it goes from tip from we don't go right over the tip, but it goes from the tip
Yes.
of one fin over the fuselage and to the tip of the other fin with a single fiberglass strip. This is just
Yeah.
to even out the filleting part so that it doesn't kink over there.
Okay.
Now I will talk about the bow tail.
Okay.
Yes, the shape was circular arc. For the bow tail, we used the NECA, I forget the document now, but was based in the NACA manufacturing, not manufacturing, I forget the word now, is NACA memorandum. Yes, this is NACA memorandum that we used to design the boat tail, and we designed it for 0.6 Mach. Yes, Mach was the velocity that we thought that was property to design it, and I think it's just this, and the manufacturing of the boat tail was the same as the nose cone. Yes, but it's a little bit easier because we don't have we have all the two sides of the boat tail are open. Yes, and it's easier to manufacturing it. So we use the same, and the vacuum elimination is to it becomes lighter. Yes,
Okay.
you can show the next slide.
Okay.
Yes, now I will talk about the fuselage. We use the manual fiberglass layup on tubular mandrel. With this, Juliana is showing you the tube, yes. And we use the fabric with the fiber oriented at 45 degrees and minus 45 degrees because it's the better uh, for our case that design rockets, yes. And we use the epoxy resin to to do to the structural function, yes, about the fiberglass and resin, and it becomes stronger, lighter, yes. Now we'll talk about the couplers that we use in the tubes. Juliana and Caio are showing it to you. They are machined out of aluminum 6351 and T6, yes, aluminum. And they are male and female system that is a pair that how the name says is standard, so we can change in the tubes if we need. But it's like a male and female to becomes a modular one and to be easier to attach it the modules of the rocket. Yes, and the bulkheads are bolted to internal flange. Yes, show him kind. Yes, you can see the bolts inside it. Yes.
Okay.
Like this.
Works very
Yes.
good.
Yes. About the recovery, we have a coupler in the recovery system. Yes, so it can slide about the slide in the tube, and we can do the recovery. The coupler is made out of fiberglass and epoxy resin, same as boat tail, same as nose cone, and the tube, the fuselage. And we attached it in the fuselage with the arrowjig adhesive. Yes, it's the same that we use in the couplers in the fuselage too. We have the motor tube coupler. The motor tube is separated in two parts to facilitate the packing of the fuselage in the bags. Yes, and with the fins, it's a little bit hard to transport it. The coupler is made out of fiberglass and epoxy resin, and it has one diameter of interface in each tube. Yes, is the recommended in the manual. Yes, to be this higher the length of this coupler. And in this tube, we don't have like a structural purpose. Yes, because of the motor chamber and another parts of the motor have the the structural function in this case.
Mm-hmm.
Yes.
Looks good.
Yes. And the last part, I think, is the rail attachment. Yes.
Right.
It's made in the airfoil shaped rail button
Mm-hmm.
and attached with the couplers with bolts. Yes, so we screw. And we made nowadays we use it to manufacture our our real buttons. Yes, but I think for the sake of we bought some properties for the competition. Yes.
Okay. Excellent.
The final part is the structural analysis. We do the structural analysis with ANSYS. Yes. There we're showing the mail of the couplers and the U-boat section in the recovery module. Yes, there are some parts that have some forces action in it. Yes, the safety factor it's okay. The part that was worst, I think, has like a safety factor of 3. Yes,
Mm-hmm.
so it's okay. That is the coupler of the motor. Yes, because the has the thrust and the inertia of the body that's over the coupler. I think that is it.
That's the end of our presentation. Jimmy,
Okay.
if you have any doubts, can can make these questions now.
I'd like to go back to the aft end of the rocket with a boat tail. And my question is, what is your motor retainer? What holds the motor in the rocket?
Oops, sorry. I forgot to put in that image, but we have a special coupler.
Okay.
I'm really sorry.
Oh, that's
This
okay.
this is it. Let me just turn on the cut here so you can see it better. Where is the cut? Okay, here. Uh,
Tá carregando.
yeah, it takes a bit of time to load.
Oh,
Okay,
no rush.
now you can see it
Just wake
clearly.
me up when it's time.
Caio, calma aí. A gente. Sorry, we were talking in Portuguese because we had a problem here. We're sharing only the
Oh.
Google Chrome tab. We're not
Yeah,
sharing.
we're,
We're not
we're
sharing
sharing
the
the wrong
CAD.
tab.
No,
I'm
the
sorry.
rocket. Sorry. Just a minute. Just a minute.
Pode dispensar aí. Trocar de...
But they will show to you. But it's a coupler that stays like in the ends of the rocket. Yes, and it's attached to the motor body and the boat tail, and it has like the same diameter as the motor. So with the friction, it can align the motor, and the motor is screwed. The upper part of the motor is screwed in the coupler. Too.
Yeah.
Okay.
Yes.
Here you can see in pink or salmon or whichever colors it is. This is the forward closure of the motor,
Okay.
and
Yes.
it is attached to directly attached to this coupler here, which is sort of a double coupler. It works as a female coupler on the top side, and it has a centering ring here.
Okay.
So it holds the motor by the forward closure, and the motor tube. This tube actually suffers no load or little load because it shares the load of the with the rocket structure itself. And here on
Okay.
the bottom we have another centering ring here in cyan that holds the motor and the fuselage together.
Okay. So that bottom ring is also holding the motor in, right?
It's more. This is more of a centering ring than a retaining ring.
Okay.
Because the here the casing is holding most of the load rather than the fuselage, because you have almost no weight here behind the motor, because the motor is
Right.
pushing the upper frame with the bulkhead. So the casing is supporting the motor here, and this
Okay.
just attaches the motor to the fuselage to keep it appropriately centered.
Okay. Well, the two concerns are first off that the motor can't fall out, which pretty obvious that it won't. You've got a lot of screws holding it in from both ends, right? Right.
Yeah,
The other one is the other concern is how is the thrust of the motor transmitted to the rocket? And if you go back to that head end, if can you zoom on that again for just a moment? Yeah, where they couple together. I haven't examined this closely, but it looks like your major thrust is going to come through that coupler.
yeah.
And is it just the screws that are keeping the motor from going forward, or does it impinge upon a flange or something within that coupler?
It's just the screws, but it's 12 M5 screws, and
also the friction between the.
yeah, like we can also talk about friction, but just getting on a worst case scenario, it's a bunch of M5 screws, and that's the strategy that we have used to hold the motor in previous launches as well.
Okay.
It has held up with no problems.
Okay, so you've done this before and it's worked okay with the
Yeah.
same size motor. Okay, then I'll go with it.
It's the this line of screws here,
Yeah.
and it works just fine.
What I would suggest, if you want a little exercise and you have not done this yet, do a stress analysis on that junction.
I think we have
We
done,
had.
but
Yes.
we
Have you
like
done it?
there's a chance that we might have done it before the new thrust curve.
No, no,
But
no.
safety factor is way up the roof, so
It's updated, kind of.
it's
It's
up. Oh,
updated.
so it's
Yes.
up.
What I talk about the safety factor that was 3 is it was in this case. Yes, is the female coupler that is in there that goes the 12 bolts and 5. Yes, in this case, and the safety factor it's okay in this case. Yes, so we simulated it.
Okay, so you've done a simulation, the safety factors
Yes,
acceptable. Okay, I'm satisfied then.
it is there in the technical report is in there. Okay, if you
Yeah,
want to
I
see.
didn't read all your
No,
appendices.
it's
It might
okay.
have been there.
It's okay, but I was just saying if you were curious. Yes.
Yes. Well answered question. Thank you.
And just as we talked previously about the twisting of the shock cords. Você tá
Oh, yeah.
WhatsApp open? Tá com WhatsApp aberto? No. Oh, okay. I will change the. I'll share my screen because I have the pictures that I told you about from the tangled shock cords from last year's launch.
Okay.
And I can show you that to let's see, window here. Okay, so you can see the tangle, the twisted
Okay.
oblivion shock cords.
Yeah.
So yeah, this was a sad day for us, but the good news at least was that all the wiring held up.
Okay.
I
Okay,
have,
but I would not trust it to hold up another time.
okay, yeah, I'll work on the method that you said of the zigzagging and tying up with something that can release in case of excessive tension. And just to add another layer of safety to that, because it's a really hard moment of flight to simulate because it only happens up there.
Yes.
And yeah, here I have a closer up picture of how it's set up. You can see that the strands here are burned. So
okay, good.
It did cut the control line, but yeah, it's all tangled up, and it was tangled up on the parachute, as you can see here. The darker colored control line tying up all the suspension all the shroud lines.
Right.
But we have since fixed it because you can see the swivel link right over here, which caused us that problem. So it has since been fixed. We're being extra careful with it now. All suggestions are welcome because you can never be too careful.
Yeah.
So yeah.
Well, you can. If you're too careful, you never do anything.
Yeah,
But you got to be careful enough that you can do it again and again and again.
Yeah, we like to move, one step at a time.
Yeah, yeah.
But this is the thing that we have been doing for quite some time. We figured out we were lucky with the tangling of the shock cords in 2022,
Yeah.
because the winds were a lot lower compared to Spaceport, in which you have way higher winds, and then that problem came to us in a bad way. But we done the tests. We thought about it. We brainstormed options, and I really hope we figured it out.
No. Looks like you're doing real well with it.
Thank you.
Yeah.
So, do you have any extra questions?
I do. A quick glance at my notes, see if I missed anything. And okay, covered all that. Covered all that. Covered all that. Covered all that. I think you covered it all.
Great. So I have one question / invitation to you regarding that problem we had back in the first progress report with the simulation software, that we sent the output of Rocket Pi and it was confusing.
Yeah.
We talked about that with the development team.
Yeah.
And do you mind if we ask you to share your opinions on how to improve it, so that we can make a good export function, so we can, like, we simulate in that gibberish language, and then we can print it out to a more human readable PDF.
Oh yeah, definitely. Put me on board for that.
Okay, thank you very much then.
Send me whatever, and I'll try to gibberize it.
Okay.
I'm pretty good at gibberish myself, as you've observed.
All right, that's great to hear, so that we can improve it and not have these kind of issues in the next competition, hopefully. Okay, so
Any questions for me? Other questions? Comments? Rude remarks? Nothing too insulting.
No, not at all.
Well, you guys are so good. I'm really happy to be working with you, and
it's a pleasure to work with you too. We hope we make your job as easy as you make ours.
Okay. It's fun. It's fun for me.
That's really good to hear.
Yeah, and I haven't made sugar motor in years. I'm just dying to see yours work.
So are we. We'll see each other. I think most of the team, everyone on this call will meet you.
Except for me.
Except for Juliana, which you met last year.
Oh.
But except for her, everyone we hope we meet on the competition.
Yes.
And I think it'll be a great time.
Yes, it will be.
So,
well, thanks to all the presenters. You did very well. And thanks for putting up with doing it in English. Sorry, that's my only language.
Okay.
But you did great.
Thanks. I'm going to stop the recording here, all right?
Okay. Are we done?